No, but seriously, the stuff we're going to do today with the unsupervised learning is a bit more nuanced. Everybody loves the supervised learning because it's like it's super fun. And the thing that we probably forgot to tell you, or if we didn't forget, somebody else will forget to tell you, is that you have to have labeled data to do supervised learning. And labeled data is actually rarer than you might like. Really, when you're doing this stuff, you do a lot of these unsupervised learning techniques. And as I said, they're a bit more nuanced. There's a bit more art to them. And so I'm going to spend a little time explaining how these actually work, so you have a little deeper understanding, and that will help you apply it. Okay, so first, we're going to talk about clustering. So what is clustering? That's a great place to start, I think. So as I mentioned, this is an unsupervised learning technique. Okay, so there's no labels necessary. You can have labels, it's okay. You can cluster things with labels, but you don't have to have them anymore. Okay, so this idea where there's some column we're trying to predict, just forget all that. Okay, you can just have data. Okay, it's useful for finding similar instances. In fact, that's pretty much all it's useful for. That's not entirely true. Okay, you can do some kind of smart sampling and labeling. I'll explain all this. But really what's happening is we're finding self-similar groups of instances. And when we're talking about similarity, we're just taking a data set and we're saying what things in here look the same, that you can put together, find groups in here that things look similar. So you can imagine customers, if you had some kind of customer data, that you would be finding customers that have similar behavior. Maybe they're clicking around a website. And so when you cluster them, you're going to have customers that are all clicking around in the same way or buying the same kinds of things. That's what you're doing with clustering. In a medical context, you might be clustering diagnostic information, so you're finding patients with similar diagnostic measurements. All right? So each of these groups that we're going to find, the output of these algorithms, is going to be defined by a centroid. So the centroid is the geometric center of the group. All right, so you can imagine that if you're grouping patients, they're not all going to have the exact same diagnostic measurements, but you're going to be able to say there's this kernel, and all these patients are pretty similar, and you're going to define that group by the middle. You're going to represent the entire group by the geometric center. They're all in this range, and so the center is this point. Okay? It represents the average member of that group, if you will. In some ways, it exactly represents the average. And then the number of centroids is another thing that linguistically we're going to be talking about. And we'll call this K because that's just a great letter. And it can be specified or determined. Okay, you can say I want 3 groups, or you can say I don't know how many I want, find the optimum number. Okay, and then there's some sense of finding the right number of groups for your data. A little different puzzle. Okay, so just so that we're clear, here we have some transactional data. Right, so we have things like the date, which in this case is just the day of the week, and we have the customer and account number, the kind of authorization they used, right? Did they sign a receipt or they use a PIN or something? And there's a class, maybe we've classified these purchases, right? And there's some kind of a zip code and the amount that was spent, all right? And when we're thinking about clustering, what we're looking for is like those 3 blue rows, all right? They're somehow similar. And the way they're similar is that they use the same kind of authentication, and they all have an amount that's around $100. All right? And they're different, though. You'll notice they're not exactly the same, right? They're on different days. They're different customers. They're different account numbers. They're for different kinds of purchases and different zip codes. Okay? But we could group those. It's one way we could do it. And obviously, part of the algorithm is to find the right qualities for grouping these things. But this is one way you could think about how these transactions have some self-similarity in them. All right? And if this was a cluster that we discovered from clustering, we would define the centroid, okay, member as the average member. Well, so for a categorical thing, the date is going to be Wednesday because 2 out of 3 of those is Wednesday. It's the most common class. So that would be the centroid would be Wednesday, okay? And the customer would be Bob because 2 out of 3 of the transactions are for Bob. And the account is 3421 for the same reason. All right, so in these categorical values, you're taking the most common class. For the numeric values, you're going to be taking an average. Okay, so the amount is 104, which, if I've done it right, should be the mathematical average of those 3 amounts. Okay? So what would you use this for? Right? It's probably a good time to ask that question. So one idea is just customer segmentation. So you just start with a data set that's full of customers, and you just want to know what kinds of customers you have. You don't even know what you're going to do with them yet, but you know that whatever you're going to do, you want them segmented. You want them in buckets, right? These are all my customers that are similar somehow, but they're different from these ones. Which customers are similar? How many natural groups are there in your data is a good question to ask, right? Maybe you just have one kind of customer, maybe you have 15 kinds. Do you know, right? Clustering is one way you can find this out. There's an idea of item discovery. So what other items are similar to this one? So maybe you have some kind of a product database and you pick one out and you go, okay, I know what this is like. What are other products that are very similar to this one? All right, in terms of, cost or application or classification. And more in the similarity vein, what other instances are sharing a specific property? You can make a recommender, and I say almost, but you really can. I mean, it's not the way people, if you Google recommender, you're going to start going down a rabbit hole of the very specialized algorithms. But you can actually make a recommender with the stuff that we're showing you, okay, with some clustering techniques and some simple modeling, you can do it. It's just not going to be what you read about when you read about recommenders. Okay, but if you like this one, what other items might you like, right, by similarity? And active learning is another fun one too. The idea is that, as I mentioned at the start, more often than not, in the real world, you tend to have unlabeled data. And then one of the very first things you're trying to do is label it. And labeling can be very expensive. And clustering is sort of a way you can cheat and make labeling cheaper. All right, because you don't actually have to label everything. If you know lots of things are the same, you can just take one out and label it and say, that's all of them. And it's a bit unfair, sure. But if you're talking about a billion things, it's pretty optimum, okay, rather than trying to label a billion things. Okay, so a little clearer on this customer segmentation idea. So imagine you have a data set of mobile game users. So you've got some mobile game app, and you can imagine that you're playing the game, and eventually the game pesters you to buy something, right? You got to buy a level upgrade or something. And so your data for each user consists of the usage statistics. They installed your game, they played it for an hour, and they never played it again. Or they played it for an hour every day at 8 a.m. for a month, okay? Or they played it nonstop for 3 days without sleeping. That's the kind of data you have about your customers. And you also know what their long-term value was based on how many levels they purchased or whatever else they bought, okay? And your assumption in your mind is that that early usage is going to correspond to that long-term value. How you use it on day one is going to somehow correspond to how much money you're going to spend over the next 3 months, all right? And so the goal is to cluster the users by their usage statistics. You want to sort of bucket these all together. You want to say, okay, in the first week, this is what my customers did. They installed it in the first week. This was what their usage pattern looked like. So all these new customers I have, I only know, so I've got old customers I know data for a year. I know how much they spent. The new ones I only have a week. So I want to find what customers they're similar to so that I can say they're probably going to spend that much too. Does that make sense? Yep. So if they have a similar usage by clustering, then I assume that they're going to have a similar spend by long-term value. And so now maybe I can, give them a deal or offer them a special and encourage them to buy earlier so I can drive my revenue. Okay? And so maybe we'll end up with some kind of a group down here where we say, these customers are 3%. So these are groups of customers by usage. And these ones, 3% of them have a high long-term value. And this group over here is only 1% and 0%. These customers are the ones that never buy anything. And so if I'm thinking about, offering specials, maybe I offer them to that group, right? Because there's a higher percentage of potential long-term value customers in there. Okay, maybe there's a cost to offering these deals, so you don't want to do it to everyone. Okay? Thinking about similarity. Do you guys know about Lending Club? Is that a thing here? I can never remember if it's. How about just peer-to-peer lending in general? The idea that if I decide I just have too much money, then I can loan it out to risky people I don't know on the internet. You familiar with this? Thank you. Yeah, okay, so you go on there, and it's super fun, actually, and they make their data public, which makes it even more fun. But you can go on there, and there's people that just say, I want money to buy a boat, and you can look at their credit information and what they want the money for, and you can say, sure, I'll fund that. You need a boat. I totally believe in you. And then they pay you back. But it turns into a whole secondary market where you can actually go and buy the loans from other people that funded them. So there's people that identify the good ones, and they fund them, and then they just turn around and sell them for like a percentage. Yeah, so you don't have to do the legwork of finding the good ones. It's very interesting. But I have this data set of Lending Club loans. I think we'll play with it a little bit today. And the idea is that it's a very similar behavior pattern. I can look at the history of loans, and I can see customers that paid their loan and customers that defaulted, and I know things about their credit and things like that, right? But as a new customer, I don't have that information yet because you haven't paid the loan, right? I don't know if I had 6 loans that you never paid, I could say, yeah, you're not going to pay it, okay? But what I have is data about what other people have paid and haven't, and maybe you're a new person. And so I can cluster your behavior, all right, by your application profile and put you in clusters with similar applications, similar debt-to-income ratios, similar customer profile information, similar income, things like that. And I can rank all those clusters by how many troubled loans there were, right? So these are all loan applications, and this one here is 7% of them are loans that just never got paid, you know, and this one is 3%, and that one's 1%, and that one's 0%. And so, you know, which group, if you didn't know anything else, which group would you want to start shopping in, right? Probably not the 7% unless you just enjoy risk. Yeah, so this is a way to, you know, you could argue perhaps unfairly, to make some kind of a claim, but it's statistics, so there you go, about what the potential risk is for these loans at the outset, even though it's a new person you don't actually know anything about yet. Okay? Okay, so this idea of active learning. So I stole this picture from somewhere. I should make my own. That's not a very good one. But the idea is that you're kind of helping the computer, okay, do a better job of doing this machine learning idea. So imagine that you had a data set of diagnostic measurements of 768 patients, and I love this because I have that data set. And it's a very silly, the diabetes data set, but that's okay. So imagine that you have this data set, like I do. But let's say that we didn't have the label, okay? We just had the diagnostic measurements. We didn't know which of those patients had diabetes or not, okay? We just had 768 people come through, we took their blood pressure, and we took 2-hour plasma glucose, and it's just, you know, some nurses or something, and they just collect all this data, and you're like, fantastic, now I need to know which ones have diabetes, okay? So I can build my cool model. But now I need an expensive doctor. I need a doctor to survey every single patient and tell me which ones have diabetes, which one don't, right? And that part could be very expensive, okay, if I'm not the doctor myself. And so, you know, you could imagine doing this with sampling, right? I could just kind of sample, but we want to sample intelligently. And one thing you could do then is you could cluster all these patients together, and rather than sampling randomly, you're going to sample from those groups. So you're going to end up with clusters of patients that all have very similar diagnostic profiles. They all look very similar. Okay, in their 2-hour plasma glucose and their blood pressure, triglycerides, they're all very similar. Not exact, the same, but similar. And you're going to take a few patients from there and test them, and you're going to say, well, you know, these patients from this group, they all have diabetes, and so the rest of them in that group, they probably do too. And then you can just apply that label to all of them. And yes, we're generalizing, but the whole machine learning process is generalizing, and so it's not cheating in the way that you're thinking it is. Okay? And this is a simple example. If you'd like a more realistic example of a high-cost situation, imagine you have a data set with 1 billion transactions. Okay? And you need to label each one as fraudulent or not. All right? Or 1 million images, pictures that somebody has to look at each one and decide if it's a picture of a cat or not. Right? It's the classic internet meme. Okay? This is a very expensive process, right? To look at 1 billion transactions and go, that one's okay, that one's not, that one's okay. It's going to take forever. You're much better off doing some kind of approach like this where you sample and reduce the size and say, you know what, of this 1 billion transactions, sure, it's 1 billion, but 10 million of them are exactly the same, and they were all fine. And so I'm just going to call that whole group fine. If there was one fraudulent in there, I didn't even care anyways because it was $5. All right? And so you can sort of filter out this data set with clustering and do this smart sampling and label it. Okay, very useful. And now again, hopefully you're thinking about how this is turning into a workflow, right? It's not always just a beautiful, clean data set, do something great, and move on. It's a bit more nuanced. So item discovery, this is what we're going to do because it's super fun. Even though somebody put this talk in the morning, so I have to talk about whiskeys at 9 in the morning, that's okay. So I have this data set of 86 whiskeys, all right? And each one is scored on a scale from 0 to 4, so the numeric values. And there's these 12 possible flavor characteristics. Does anybody in here drink scotch? You guys? Just a few hands. Okay, did you know that there were 12 possible ways you could describe the flavor of a scotch? Did you know that? No? Okay. It's a very interesting world. Professional scotch drinkers, I guess. Okay, so what we're going to do, though, is we're going to cluster these, all right, by the flavor profile. And what this is going to do, then, is find whiskeys that have a similar flavor profile, right? So now I can start saying, these are the fruity whiskeys, and those are the smoky ones. And this could be a process whereby I can say, well, I really like this one. What's another one I might like? And now I know, because I know that there's 5 other ones that are very similar flavor profile. Maybe not exactly the same, but similar. All right? And because it's such a great data set, we're going to have to do it. I haven't done this one in a while, so we'll see if it goes well. It just occurred to me last night. I haven't clustered this in a bit. Okay, let's see if I have this here. And, no. Okay. Well, I do have it in the folder, so we'll do that. It's an extremely small font. Where did you go? It will help if I actually find the data. Bear with me for a moment. Let's see, Google Drive, maybe. Maybe here. Oh, yes. Okay, we're winning now. Okay. Oh, that's a little big, isn't it? All right. Okay, so as advertised, we have these 12 flavor profiles, right? Floral, fruity, malty, spicy, honey, tobacco. Did you know it could have a tobacco flavor? That's an odd one, I think. Smoky, that should be pretty familiar with anyone who's ever had one scotch, at least in their life. And we do have a text field up there. It's a text right now, which is the distillery. And we're going to largely just ignore that, okay? I mean, you could think it's a label, but it isn't really in the sense that we think of machine learning labels, because it's distinct for every whiskey, right? It's a different value for every single one. So it's not really a class per se. It's exactly the name of each one. Okay, well, actually, let's go ahead and change that. We can make it a category. Why not? It won't hurt anything. Okay, so we'll do our one-click data set, and we'll explore what these flavors look like. So again, you'll notice that every single value in the distillery is different, and there's a little red exclamation mark. I'm going to try to remember to tell you more things that we haven't told you yet. So that's one. When you create this data set, one of the things we do is we run a little heuristic that tries to determine whether or not this feature is going to be useful for machine learning. Okay? And anytime you have a value that's distinct for every single instance, it's probably not useful for machine learning. Right? It just has too much variance. I mean, you're not going to be able to generalize from that information, like a patient ID or some kind of, in this case, a name that's unique for everyone. There's nothing you can generalize from that. Okay? And so it marks it automatically as you probably don't want this feature in here. Okay? So that's a nice little feature it does for you there. Yep. Yes. Okay, well, fair enough. Yeah, okay. That's true. Yeah, it could be a unique numeric value. One would presume. No, well, I mean, no, come on. Number of bedrooms in a house. Okay. Let's make a cluster, though. That'll be more fun than talking about pedantic things. Okay, so what we're going to do is, under the gears there, we're going to choose configure the cluster, and I'm going to show you why we're going to configure it. You can do a one-click cluster. If you do a one-click cluster, it's going to do what I'm doing right now, but it'll do 8 groups by default. So it's going to take these whiskeys and break them into 8 groups. For this demonstration, I want 10 groups, because it makes for a cooler demonstration. And yeah, no, that's exactly why. And you could make the argument that, well, that's, why does 10 make a cooler demonstration? And the answer, and this is a completely honest answer, is that I tried 8 and I tried 10 and a few other things, and 10 did what I wanted. And you would say, well, that's a horrible answer, and I would say that's how clustering works. I mean, this is a specific case where I know the behavior I want from this cluster, okay? And so I'm going to make it do that. That's a perfectly valid thing to do. There are times when you have no idea how many clusters you want or what the behavior is, and I'm going to show you how to do that too, all right? And I'm also going to turn on this thing called modeling clusters, so we'll play with that a bit too. But that was enough explanation of that. So this is going to go ahead and run. Okay, and now we have all of these groups of whiskeys. So what you're looking at in this, each one of these little discs represents a group of whiskeys, okay? And visually, when you have one highlighted, like this red one in the middle, these groups that are nearby are somehow, their flavor profiles are nearby that one that's in the middle. And you see this one that's floating out here. It's not nearby. Okay, it's a very unique flavor profile to the rest of those in the middle. And if you pick any one of these and click on it, it puts it in the center, and you can see how the rest of them are distributed. Because remember, this is like a big 12-dimensional space, so we're just looking at a two-dimensional view. So we're looking at distances. So in this visualization, these two flavor profiles are somewhat close to that, and the rest are really far away from that one that's highlighted. Okay, and for any one of these, I can freeze it and see what the qualities are. All right, so I can see that that group of whiskeys all has a body of close to 4, all right, and a sweetness of close to 1.5. Okay, and these other features, I can learn what the centroid of that group is. Okay, and that's pretty much all there is to clustering. Okay, there's lots of things we can do with it, so we're going to do a few more things. Don't panic. One in particular is it might be super nice to understand this group a little bit more, okay, than just talking about the center of that cluster. And that's why I clicked on the model cluster. So any of these groups you pick, you can highlight it, and then you click this little button down here. And what it's going to do is use those cluster groups as a label. So we've just labeled this data set. The label is the cluster they belong to. So that was cluster 4. So these are all the cluster 4 whiskeys, and everything else is some other cluster. And it just built a tree that tells us the properties that differentiate cluster 4 from everything else. So this tree tells us how cluster 4 is different than the other whiskeys, all right, which is kind of a neat little trick. And if I'm honest, it's not always this clean. You don't always get a decision tree this tiny and short, but you can also do association discovery, all right? We won't have time to do that in this session because we're not doing association discovery, but you do often, or sometimes get trees like this, and you can learn very quickly that what distinguishes this group is this medicinal quality. If it's greater than 2, it's in this membership. So these are all the whiskeys that have a very strong medicinal flavor. Okay, that's a very strong pattern for membership in this group. All right? And likewise, even if it isn't medicinal, okay, if medicinal quality is less than or 2, you see it's also splitting on the smoky. And if it's greater than 3, okay, very smoky, then it's also in this group. So these are the whiskeys that are medicinal or smoky. And by or, I mean the traditional non-exclusive or. Yep. Okay. If we wanted to actually think of this as a labeling project, we could actually go ahead and label our data set with these memberships. So you can do it with a batch centroid, all right? And I can just pass it the data set. And what it's going to do is take this data set and run it through this cluster and assign the label that each one of those members belongs to and make a new data set. Okay, so when I output this data set now, I have all of the original data plus the label that we've just learned. Okay, so there's 9 that are in cluster 0 and 14 that are in cluster 1. And if I download this as CSV, there'll be a new column, which is the cluster membership of each one. Okay, so I can now see all of the cluster 1 whiskeys and all of the cluster 3, okay, individually. Make sense? It's a little early in the morning for heady things like clustering, but okay. Let's talk about how this works, because it's actually kind of fun. And then I'm noticing I'll have to speed up a little, so I apologize ahead of time. So let's does anybody know how clustering works, by the way? This k-means algorithm? Anybody already know? Oh, fantastic. Well, this will be fun. Okay, so here's a set of objects, and these are actually objects that I found on my desk at a phase when I had younger children, so that's why they're so random. That's a true story. And I actually took each of my children, well, the 2 that I didn't think would eat the battery. There was a 3rd that probably would have eaten it, so he didn't get to play. But I said, please cluster this into 3 groups. Take these objects and put them into 3 groups. Okay, so if you want to take just 10 seconds and think about how you would make 3 groups, it has to be 3. You can't have 6 or 12, that's cheating, it's got to be 3. So you got to put these into 3 groups, okay? Yeah, that's all you get. They had more fun. They were moving things around the table, it was a good time. Okay, so this is my middle daughter, it's Jessa, picture of her in the corner there, and these were the groups that she came up with. Okay, and I wasn't done with them. I said, okay, that's fantastic. Now you have to tell me what these groups are. I want to understand your thinking. All right, but that was how she arranged them. And what she did is essentially she used her prior knowledge about the physical objects in the world, okay, to select possible features that separated these objects. She didn't say it this way. How cool would that have been, right? Right? That would have been great. I used my prior knowledge. No, she didn't, but that was what she did. And what she described was things that were round or somehow skinny or had edges, and things that were hard. Those are the groups that she made. Round, you know, those ones in the upper right have edges, and those ones down there are all skinny. Okay, those are the properties that she identified. And then she clustered them based on those chosen features, right? Because some of them have some of them match both of those characteristics, And so she went by which ones were more likely. Yeah, and the separation quality was then tested to ensure that she met the criteria of 3, because she did a lot of sorting to make sure there were 3, and that the groups were sufficiently distant that you could really tell them apart. And if you look at that picture, the ones that have edges are pretty clear. They look different than the ones that are all around. Yeah, you agree? Okay. And there was no crossover. Okay. So and then I had to make a slide out of this, so I had to start thinking about the features that she described. And so I invented the length divided by the width ratio, all right, which is very nice because it defines both skinny and round. Okay, if it's greater than 1, that's a skinny object. If it's equal to 1, it's round. If it's less than 1, then it's still skinny. I just measured the wrong way. Okay, so that separates skinny from round very nicely. And then you could talk about kind of like the number of surfaces, right? Distinct surfaces require edges, which have corners, because she was talking about edges. But surfaces are easier to count, right? So you could look at a cube and you can go 1, 2, 3, 4. You can count the edges. Okay, but a penny is just 1, 2, and 3. There's only 3 edges. Okay, so easier to count edges. And so if you do that, you can create features for these objects, and they would look like this, right? So there's the penny, has a length-width ratio of 1. It has 3 surfaces, 1, 2, and 3. The key, I had to cheat a little bit, but the length-width ratio is 4, and I went ahead and called that 3 surfaces, because otherwise it has like 97 or something, right? It's a bunch of little notches. So we just called that 3. That was okay. All right, and now what I want to do is I want to just plot these. We'll just put them on a graph. We've got 2 dimensions, so it's very easy to look at, and this is real. Okay, this is what it would look like. There's the box, the block, and the eraser. There's the knob, the penny, and the dime, and the bead, and the key, the battery, and the screw. Okay, they're all on there. And if I asked you now, looking at this, to put that into 3 groups, it'd be pretty easy, right? Okay, now my youngest could do it, because unless he eats the paper, you just give him a crayon, and it's really easy. Okay, it's not as easy for computers. They have a little bit more trouble because they're not as visual as we are. But you can see that with these features, the way she described them, this is very clear how we would cluster these. And so the k-means algorithm, what we want to do is come up with a way to take this clarity that we see in the grouping and make it algorithmic. That's what we want to do. All right? And so here's how it works. The first thing that k-means does is it says, oh, you want 3 groups? Well, oh, sorry. This is what we want. This is where we want to arrive. These are the groups, and the black dots are the centers. That's where we want to get to. Okay. So k-means is going to find the minimum distance. Okay. So k-means says, oh, you want 3. There you go. There's 3. Here's 3. You wanted 3. There they are. Okay, those aren't the 3 we wanted, right? So then you say, okay, try again. And it says, okay, here's the catch. I'm going to get better every time I do it. I'm not going to get worse. I'm never going to get worse. I know what you want. This is just a guess. I'm sorry. It's terrible. But the algorithm is going to try harder. And so what it's basically going to do is measure the distance from these points to all of the points in the data set, the centroids. It's going to measure how far away they are, okay? And then it's going to move them closer to where there's essentially, if you want to think about it like more mass, like think about like a gravitational pull. Okay, so that one that's connected to 4 things there is going to move towards the 3 on the left because it's sort of attracted there, okay? It's not a gravitational pull, but that's an okay analogy. Okay, so that one's going to move that way, that one's going to move towards those 2, and that one's going to move towards those 3 at the top. It's just going to move them closer to those points where they're closer. Okay? And then it's going to try it again, and it's just going to keep doing this until those dots stop moving. Okay, eventually, you're going to reach some kind of a minimum, and the dots aren't going to move anymore even if you run the algorithm again. And that's it. The centers have been found. Okay, there's some caveats in there. Features matter. This is my other daughter. And she found a different grouping. Okay? She said those ones are all metal, those were wood, and those were other. Very straightforward measurement. Okay? So the features do matter for this puzzle, by the way. I probably don't have to belabor this too much. K-means does converge. If you're grouping these 4 dots, you're not sure which group you're going to get. You're going to one of these, you'll get that one or that one, but it's going to find one of them. It's not just going to labor around trying to decide. It's going to say that's the group and stop. Okay, so it works pretty well. Okay, so starting points are an issue. I probably need to zip through this. Okay. There's a risk of suboptimal convergence. Don't worry about it. You'll never see it. Okay, this is kind of fun though. We are a little smarter about how you choose the starting points. How you choose, remember I just said here's 3 dots. Okay, if you do it that way, you can get into some trouble. And so we actually use a technique that's called K++, or maybe a variation on this, and for choosing those starting points very carefully. And I still need to reword that sentence. It's horrible. So I did pictures because I couldn't figure out how to reword the sentence. So these are our data points that we want to cluster, all right? And what you're essentially going to do is just pick one from the data points. You pick a centroid that is a data point, and then you start looking at distances from that centroid in terms of probabilities. So you're going to choose the next one with a low probability. You could choose one from that group, but with a low probability, and one from there with a high probability. And that's the highest. And so maybe we get that point over there. We're still looking for 3, so we need one more. So we do it again. Those are low probability choices, and so maybe we end up with one down there, and those are our 3 starting points. So that's just a clever way to make sure you don't get weird outliers, and you don't pick your 3 starting points all right next to each other, so the algorithm takes forever to converge because they're wandering around and eventually moving. Okay. Scaling matters a lot. Like if you're doing cluster of homes data sets, you have like the number of bedrooms and the price, and you see the scale there, is hundreds of thousands, and the scale here is just small integers. And so the distance there between those 2 red dots is 1, and the distance between the red and the green is 160,000. That matters for this algorithm because it's talking about distances. It matters so much that we do the scaling for you automatically. Okay, you can turn it off if for some reason you just want to have scaling issues. That's cool. But we take it out. We normalize all these things for you. Okay, you could think about other things that we do for you. What is the distance to a missing value? What is the distance between categorical values? How far is it from a red to a green? Okay, what is the distance between text features? Does it have to be a Euclidean distance, right? So far, we've just been thinking about distances. And what is the ideal number of clusters? And I'm going to skip through a little bit of this, I apologize, because we do this for you automatically. But you can't really do a distance to a missing, so you have to replace missing values. That's one thing that does trip people up in the clustering. By default, the default action, if there's a row that has a missing numeric value, okay, when we're clustering, we just go, don't know what to do with it, and throw it out. And then you can change that behavior. But if you happen to have a data set where every single row has one numeric value missing, then the cluster just goes, there was nothing to do. I don't know what to do. Okay, and you can change that behavior when you're clustering. When you configure the cluster, there's a default numeric value there. Okay, so if you have missing numeric values, you can say, okay, for any row that has a missing numeric value, I want you to use 0 instead, or the minimum or the mean. Okay, you can force that choice because those missing values are hard to deal with. Or by default, we ignore them. Okay. Yeah, don't worry about this. Yeah, don't worry about that either. This is a really great picture, but don't worry about that either. Okay. This is actually a bit more fun because I think I only have an hour, so I got to still do anomalies too. If you don't know the number of k, I just love explaining this algorithm. So this is another algorithm we have for clustering called g-means. And the idea here is you don't know how many clusters you want. Okay? And so we're going to come up with an algorithm that figures it out. So imagine that this is zoomed in. There's more data set around us, but this is one of those groups that we've found. Okay? This yellow dot's a centroid, and this is all the points in the data set. It's one that we found, just one. And what we're going to ask is, what if that was 2 instead? Instead of 1, what if that was 2 groups? So we just try it. We basically run k-means on this subset with 2 things, and we let the points move around, and then we think of those 2 points as defining a line, and we project everything onto the line. That's very easy to do. And you end up with some kind of a distribution. Okay, you can see that those points would make a clump on the left, and those points over there make a clump on the right. And if we see something that looks like that sort of bimodal thing, we go, that should have been 2, not 1. The 2 is better, and we keep 2 instead. If it comes out all smooth, then we go, 2 is no better than 1, so we'll keep the 1. And you just do this for every little group, and you keep doing it over and over. Excuse me. So if you had something that looked like this, you would start with k equals 2. Maybe you'd get 2 centroids that look like that. You take each one of those groups and do this same thing with this, trying them out, right? So we take this group up here. We try this one with 2 centroids, and we try this one with 2 centroids. That one we get something kind of smooth. This one we get something kind of bumpy. And we go, okay, well, that one should just be 1, but that one should be 2. So we just run it again with k equals 3. And maybe we get that. We do the same thing. Smooth, bumpy, 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 bumpy. So keep that one, split both of those, so k better be 5. We do it again, they're all smooth, we stop. That's the basic idea. Super cool. So if you want to do that g-means, you can do that. It's right there. Excuse me. This data set isn't as good for g-means, so let me show you another example. I'm going to need this anyways. So we'll take our diabetes data set again. And this time, so this is what, if you configure it, you can choose the algorithm. So I could say G means. So the number of K goes away because it's going to figure that out. But instead, nothing's free, right? There's no free lunch. So the number of groups goes away, but you inherit this critical value instead. And I was talking about smoothness and bumpiness. You can be picky about how smooth or bumpy you want things to be. That's what that critical value is doing. Okay, it's a little Gaussian test. That's the G means, G for Gaussian. And if you set this basically, well, you can read the little description there, but if you set this closer to 0, okay, then you get more groups. It's much pickier about how smooth those distributions have to be, so it keeps splitting and splitting and splitting until they're really smooth. And if you set this really big, then it accepts really lumpy things, and so you get smaller groups in general. So you do still have a parameter, but the nice thing about this is that that default of 5 works pretty well, and so you can actually just now have basically a one-click cluster. And so if you do a one-click cluster, that's what it does. It does the G means for you with a critical value of 5, and it just tries to identify the optimum number of groups. Yep. And so this is for the diabetes data set. We get 2, 4, 6, 7, and everything else after that works exactly the same. I can introspect any of these groups, and I can extract this as a data set. I didn't show you that before, but I can take a data set, a group of items from the cluster and pull it out as a new data set, and I can analyze it individually. Okay. Excuse me. Okay, so unsupervised learning technique for finding these self-similar groups. Number of centroids can be imputed or computed. You can choose. What you get out of this is a list of centroids, okay? You've got k-means and g-means to choose from. And for the cluster parameter, you either have k or a critical value. Those are your choices. And there's lots of things to do with the missing and the summary fields and the scales and the weights. And don't forget about the model clusters. The association discovery is also super cool for this. And then I did at least show you one batch centroid. You can actually do this cluster assignment as basically a labeling. Okay, so you can actually assign the cluster labels to everything in your data set, which is fun to do too. Okay, let's go straight into anomalies. Very complementary to clustering. Okay. I have too many cool things to say about these things. Okay, finding the unusual. What is anomaly detection? Well, this is kind of one of those things that you probably have an immediate visceral response to what is anomaly detection. It should feel pretty obvious, but of course we have to define it more rigorously so that we can talk about how to do it and what we mean by it. So of course, this being day 2, this is an unsupervised learning technique. Again, no labels necessary. It's useful for finding unusual things. So what I mean by that is you can use it for filtering or finding mistakes in your data. You can even do a one-class classifier, which if I have time, I'll explain at the end. It's super cool. But you're basically finding instances that do not match. So if you think about your customer data again, you're looking for a big or a small spender, perhaps. You're looking for some behavior that is different from all the rest of your customers. Okay? In a medical context, maybe you're looking for a healthy patient despite all indications to the contrary. They should be dead, and somehow they're perfectly fine. Okay, that's an anomaly. And then we define each unusual instance by some kind of score. That's the goal. Okay, we got to rank these points somehow, and the anomaly detector that we use uses this scoring system. It's a number from 0 to 1. 0 meaning that it's completely normal. There's nothing on Earth that could be more boring, okay, than that data point. 1 meaning that it's basically impossibly unusual. Okay, this is actually an exponential scale. And like a 0.7 is way bigger than a 0.6, which is still bigger than a 0.5. Okay, it's not linear. Okay, the difference between a 0.7 and 0.6 is huge compared to 0.6 to 0.5. Okay, and we can look at standard deviations and stuff too. Okay, so remember we had clustering with these transactions. We said those were similar. Okay, we have the same transactions, and so now we're looking for transactions that are somehow mystically unusual, and we might pick that one. All right, why would we pick that one? Well, because the amount at $2,459 is way higher than all the other transactions, right? It's enormous. Nothing else is even close to 1,000. It's the biggest amount. Okay, that's making that data point pretty unusual. It's also the only transaction in the zip code 21350. Okay, it's the only one. So it's the only one in that zip code, and it's for a huge amount. It's got 2 things that make it unusual. And it's also the only one for the purchase of something related to technology. It's got 3 things that make it unusual. All right, the anomaly detector, that's something we would want it to find and say, you probably want to look at this one. That's weird. All right? So use cases. You can use this for just exploration. So a lot of these unsupervised learning techniques, if you're playing with a new data set, it doesn't hurt to run some clustering, some anomaly detection, association discovery, topic modeling, if it has text fields, and just kind of see what's in the data. And anomaly detection is another good one for that too. You're just looking for, if there's anything really unusual in there. That's a perfectly valid thing. For intrusion detection, you're looking for unusual usage patterns. Maybe for fraud, you're looking for unusual behavior. Identifying incorrect data, so you're looking for mistakes in labeling, right? You might go, this is really unusual, and you go, whoa, it's just wrong. Okay, somebody put it in wrong. Or just taking out your outliers, because remember, these supervised learning models need to generalize, and so if you have anomalies in there, they don't generalize as well, because the learning algorithm is going to see those anomalies and go, wow, it looks like if your plasma glucose is just even higher, you might be healthy, because this one person was healthy. So, I mean, if you're in this range, you're sick, but if you just get a little more sugar in your blood, you're going to be fine, because I saw one person like that. Okay, so that doesn't generalize very well, so you kind of want to take those outliers out. And then we can talk about something model competence. I mentioned this yesterday, and I saw a few people give me a confused look, so we'll try to hit that one, because that's fun. Okay, removing outliers. So as I mentioned, these models need to generalize, and the outliers negatively impact that generalization. And so we can use the anomaly detector to find them and then filter them out. All right? And diabetes data set is actually a great one for this. And this is just basically to give you a sense of the workflow. You're going to take the source, build a data set. You build your training and test set. Actually, maybe I showed this to you yesterday. Yeah, I did. And you've basically used the anomaly detector as a filter there. And you take out the anomalies, and then you can model both and compare them. Okay, so you can see how the model performs. And diabetes is great for this because you take out 2 anomalies, and the evaluation metrics go up by 3%. There's just 2 patients in there that are just very unusual. And I'm not going to show you that full workflow, but I can show you those 2 unusual data sets. So let's do that. So we'll take our diabetes data set, and we'll just do, in this case, a one-click anomaly detection. Okay, so one-click unsupervised anomalies right there. And I'm going to tell you a little bit how this algorithm works, but what you get back is the most anomalous data points in there. So it's going to show you the things that were really unusual and the score for each one, but you can still use this detector like a model and run new data points through it and get an anomaly score for anything. Okay, I can use it like a model now. It is a model. Okay, so these are our top most anomalous points, and let's have a look at this one. So this is a score of 0.63. Okay, so in the UI we show them as percentages. Generally speaking, anything over a 0.6 is pretty unusual for an average data set, just so you have that in mind. Okay, not all data sets, but an average data set, anything over 0.6 is pretty suspicious. Okay, so we can start looking at this patient. Actually, maybe I want a different, oh yeah, let's have a look at this one. This is a good one. Okay, so here this patient has a super high insulin level, okay, 744, they're like the top of the scale. That's a little orange dot there, all right? Their diabetes pedigree is also right here, top of the scale, 2.3. This is a measure of how much diabetes there is genetically in your family, okay? And their 2-hour plasma glucose is basically the highest seen in the data set at a 197. It's incredibly high, all right? And they do not have diabetes. So when we built this model, that plasma glucose was like the strongest feature for predicting diabetes. And this patient has the highest, right, in this data set, and they're perfectly fine. And so there's a couple of possible outcomes here. One is that this is a mistake, right? So doctor's sloppy handwriting, and that F was supposed to be a T, and somebody wrote down wrong. So you can go now pull that record and fix it. The other possibility is that this is the luckiest person in the world, okay? Which, let's be honest, is super great for them, but we can't all be the luckiest person in the world. So this person is super bad for our model, right? Our model needs to apply in a general sense, and we can't all be that person. And so we really got to take them out. Okay, we can't consider them in this model if we want to generalize. And so we can do that. We can just take, for example, these 2 most anomalous data points, and we can just hit the button there and say create data set, and those are gone now. Those 2 patients are removed. Okay, so we totally unsupervised. We found the most anomalous points. We selected a few, filtered them out, and now we have a clean data set. Okay, super fun. Intrusion detection. This is a real-world example from my own personal history. So you can take a data set of command line history for users, right? So looking at each user that they're typing in, okay? In case you didn't know, the sysadmins can actually look at this stuff as you're typing stuff in. Yeah, they know what you're doing. Okay, so the data for each user consists of the commands, the flags, the directory they're in when they executed that command, okay? There's lots of things you can measure about where people are typing commands and how they're typing them that work like a fingerprint. And the assumption is that users typically issue the same flag patterns and work in certain directories, and that assumption, by the way, is completely true. I mean, it's fantastic how well you can fingerprint people with this. And the goal is to identify unusual command line behavior per user and across all users that might indicate some kind of an intrusion. So I would make a bunch of anomaly detectors. So I'd make an anomaly detector for each user. Okay, so I can see one day if suddenly you're typing ls-la instead of ls-al, I know you're either having some kind of aneurysm or there's somebody operating your account other than you, right? Because you never type ls-la, okay? I can make an anomaly detector for the directory you're in when you're executing that command. You type rm 16 times a day, but you never type it in the bin directory. That's a really weird thing to do today. Okay, I can do it across all users. Nobody changes into /user/bin. Okay, nobody does that. Okay, if you do that, that's weird. Or maybe across all directories. And I can use all of these anomaly detectors to build a score for everything that you're typing about how anomalous that command looks. Yeah? Super fun. Okay, fraud, same kind of idea. We can look at credit card transactions and do a card level, user level, and similar user level. I think I talked about that one a little bit yesterday, so I won't belabor it too much, but it's the same kind of idea, building several anomaly detectors and looking at how anomalous that transaction is across several different data sets. Okay, so model competence, this one is useful enough that I'll spend a few minutes longer on it. So after you put a model into production, data that's being predicted can become statistically different than the training data. Okay, this is why you have to retrain periodically. What I mean is that, let's say you run a company that makes loans or something, and you build a model that predicts the likelihood these loans will be paid back, and it turns out that while you were building this data set, nobody over the age of 50 applied for a loan, and you put that model into production, and then suddenly there's a bunch of retirees applying for loans, and their profile doesn't match your training data at all. Right, they have totally different incomes, totally different status, totally different age, totally different interests. They don't match, your model doesn't know anything about these people. It's completely incompetent. Okay, and you can measure this in real time. Okay, and the way you do it is you take your data set and you build your model. This is the thing you use for scoring, and you build an anomaly detector at the same time. Now think about what this anomaly detector is telling you. For any data point you run through this anomaly detector, it's telling you how well it matches that data set. That's exactly what it's measuring. If you run a data point through here and it gives you a high score, it doesn't match things that are in this data set. If it gives you a low score, it matches lots of things in there. That's exactly what it's telling you. So at prediction time, you run it through both of these, and you say, okay, here's a prediction, this loan is okay, and I have an 86 or a 0.86 confidence, and that one is, this other loan is okay, and I have an 84 confidence. But the anomaly score for this one's a 0.53, and that one's a 0.7. So if I look at this, I say, okay, the model thinks both of these loans are fine with a relatively high confidence, but this one that it's predicting on, it's predicting on a loan that doesn't match the training data. And so I don't know if I can actually trust that prediction, even though the model says, yeah, it's probably fine, it's okay. Okay, it's in a totally different domain of the data where it really doesn't know what it's talking about. Okay, it's abstracting from what it knows into an area where it knows nothing. Okay, and so this is a real-time measure of how competent the model is in that prediction. So you would say, no, that model is not competent there. Okay, so you do this for every single prediction, and if you see these accumulating, you're starting to get lots and lots of these, then it's time to retrain. You go back, oh, I got to get new data, build a new model so that it matches the data that's coming in. Yeah, I'll talk. Okay, this is so cool, I have to tell you. All right. So does anybody know Benford's Law? Oh, yes, of course you do. Okay. All right, so this is really strange. In real life, numeric sets, it's actually not that strange if you really sit down and think about it. But when the first time you look at this, you go, no. Numeric sets, the smaller digits occur disproportionately often as leading significant digits. So this is a distribution here of a data set that has numbers in it. And the leading digit, this is the frequency of numbers that have a 1 in them as the first digit, and the frequency of 2, and this is the frequency of 9. This is a property of data sets that have numbers in them, period. Okay, applications include accounting records. This is a real case of detecting fraud in accounting by using Benford's Law, just taking the accounting transactions, running this, and seeing the distribution doesn't match, and knowing that those transactions have been fraudulently created. Yeah. Electricity bills, street addresses, stock prices, population numbers, death rates, lengths of rivers, okay? And I can't do this in the UI, unfortunately, I have to do this in the API, but it is pretty fun. Okay, this is one way you could think about doing anomaly detection. Okay, univariate approach. You've probably seen this before if you've ever had a statistics class. but you have some kind of a single variable you're thinking about. You're looking at heights and test scores. You assume that value is distributed normally, and you compute some kind of a standard deviation. Your anomaly is the measure of how spread out the numbers are, right? So you have the square root of the variance. I'm going fast, I know. Depending on the number of instances, you choose a multiple of the standard deviations. You call that an anomaly, right? This student is scoring 3 standard deviations over. They're brilliant somehow, right? I mean, that's 3 standard deviations, huge. Okay, and it looks like something like this, and you go, here's my normal distribution, and here's 3 standard deviations, and these are all the anomalies, and those are all the anomalies as well, or outliers in this case. This would be a standard univariate approach. Okay, it can be very effective. It can also be horrible. Okay, and the reason why is that multivariate matters. So here we have a data set, and I can ask you where are the outliers in this data set, and you go that one and that one. Okay, right? Easy. Okay, but now we're thinking, remember, about 1,000 features and 1,000,000 rows, so it's much harder to visualize like this. Okay, but if we do this, if we take this distribution, on this axis it looks like this. That one's an anomaly, everything's fine. If I just take a distribution on this one's all by itself, that one's an anomaly, everything's fine. Okay, so looking at this at one variable at a time and looking at distributions is working great. You agree? Okay, now I give you that. It's still super easy to tell where the anomaly is, but if I look in this coordinate, everything looks perfectly fine. And if I look in that coordinate, everything looks perfectly fine. This data point is only unusual in 2 dimensions at the same time. It's a multivariate anomaly. There's no handy projection for those coordinates that will tell you that's an anomaly. All right? So let's go back to the human experts. Same pieces. Which one of these is the most unusual? You have to pick one. I want votes. Go ahead, yell it out. What do you think? This is screw, what? The battery, okay. What, anybody else? The key, okay, all right. So here's my eldest. Okay, she said these are skinny, those have corners, these are round. That one's just wacky. Okay, it's just a totally odd shape. Okay, so we got to vote for the key, all right. And of course, this one is skinny, but it's also not smooth. Okay, so she said that one's the most unusual because it's skinny but not smooth, it has no corners, and it's not round. So you see what she did is she made groups. These ones are round, these ones have corners, these are skinny, and this one somehow doesn't match any of those groups. And so it's the most unusual. That's what she said. And so the key insight, there's the joke, is that the most unusual object is different in some way from every partition of the feature. It doesn't matter how you slice up the features, the anomalies are the things that always stand out. Okay, I can look at them this way, and that one's still weird. I can look at them this way, and that one's still weird. Every time I look at it, it's always weird in some dimension. Okay, and so the human expert, okay, same idea. I won't belabor that too much. We use length and width, a number of surfaces, and we have to introduce a smoothness, because she talked about smoothness. And so we get things that look like this. And so now we have a smoothness here. And you see the battery, for example, is smooth, and the screw and the key are not. So we have 2 things at least that aren't smooth. And now what I want to do is just think about, I have this data set, okay? And I want to just split it the same way I was just talking about, making groups and splitting things randomly, okay? So here is, let's think about it like a decision tree. I'm just going to split randomly. So I'm just going to pick any variable randomly and split. So we'll split on smoothness first. Okay, if we do that, these are all the falses go over here and the trues go over there. Let's just split on something else. I'm picking this totally randomly, all right? Number of surfaces is 6, okay? And we split again. And look, over here we're done. We already have the key and the screw, okay? And then we just keep going. We keep going, we keep going until everything is all by itself. Isolated, that's key, isolation. Okay, so now we've just done random splits every time until everything is by itself. And the idea, oh, sorry, I should have told you the idea on that slide. But the idea, well, no, sorry. I'm trying to go fast. Okay, but the basic idea here is we're just going to do this again. We'll grow a random decision, totally random, okay, until everything in this sample is its own leaf. And basically, if it takes a whole bunch of random pieces of information to tell these 2 apart, then they're really similar. They're similar in all these random ways. Okay? I took random things and they stayed together. Random split, they stayed together. It took so many random splits to finally tell them apart. So they're somehow really similar. But these ones up here, it only took 1, 2 pieces of information and I could tell them apart from everything else. Just totally random, 1, 2. Okay? Now, of course, to do this fairly, what you're looking at, though, is the depth of the tree. All right? So if it's up here, this is anomalous. If it's down here, it's pretty normal. Okay? And you just do this over and over and over. So you do this maybe 128 times, for example, build all these weird, wacky, random trees, and you look at how deep it is in each one, and that's how it works. Okay? I'm not going to show you that one. Don't think about it. Ignore it. Okay. And I'm not going to show you that one either. I should at least show you the anomaly detector in action, though. Oh, I did already for diabetes. That's true. Okay. I'll give you one more example. This one's a bit of a brainiac, and then we're done. Okay. Let's think about a one-class classifier. This is another cool application of the anomaly detector. So let's say you place an advertisement in the local newspaper. All right? And you collect demographic information about all the responders. So people write back to you, they say, I really want that refrigerator, or they come into your store. So you know who they are. Okay, and you collect their information, how old they are, how much money you think they make. So you've got all this data. Okay, now you want to market in a new locality. So you want to go into a new city and put your ad in the newspaper again. And to optimize your mailing costs, so we're doing direct letters this time instead of the newspaper article, sorry. We need to predict who's going to respond. We don't want to send a letter to every single person in the entire city. We want to use the same demographic information and figure out who's most likely to respond and send letters only to them. We want to be very optimistic, okay, or very specialized in our. Okay, now here's the problem. If I asked you to build this model, you cannot currently distinguish people who are not interested in the product from people who never saw the ad. Do you see how that's a problem? The data set is collected from people who responded to a newspaper ad. There's lots of people that maybe would have loved to buy that refrigerator or whatever it is, but just didn't read the newspaper that day. So I can't label those people as not wanting my nice refrigerator. I only know that they either don't want it or they didn't know about it. I only have one class. I only know the people that were interested. That's it. I know one thing. Okay? This is actually a fairly common problem, not hugely common, but what you can do is you can train an anomaly detector on this data. Okay, so you take all your respondents and all your demographic information for the city. So we know things about people that didn't respond, but we don't know why they didn't respond. That's the problem. So we build an anomaly detector and then pick the households with the lowest scores. So if a household has a low anomaly score, okay, then they are similar to enough of those people that responded positively. Because remember, our data set has a label that says these are all the people that responded. And if my demographic information matches, they're going to have a low anomaly score. And all the people with the high anomaly scores don't match, and therefore less likely to respond. So I can kind of be sneaky and use an anomaly detector like a predictive model for one class. It's a cheat. Yeah. Okay, so anomaly detection is a process of finding these unusual instances. I showed you some techniques, okay, univariate standard deviation, at least I whipped through them, Benford's law. The isolation force, that's what the algorithm is called, by the way. And you can control the number of trees, and there's a few other parameters. Not super important. Basically doing a one-click most of the time is all you need. Works pretty well. In fact, actually, I should tell you, I know now I'm running over, okay. But the isolation force, part of the reason we implemented it is because our chief scientist was working on a DARPA-funded project to identify anomalous data. Maybe I won't tell you what data. And he was trying different anomaly detectors, building like a few of his own and trying different ones from the literature. And when he tried this one, it was like fantastic. And then he basically sent us an email and said, okay, you have to implement this right away. And we said, okay, we'll do that. It's actually a relatively new algorithm, by which I mean in the last decade or something. And so, yeah, it's pretty super fantastic. You can use it to filter to improve your models, find mistakes, frauds, and intruders, knowing when to retrain, and maybe you can even use it as a one-class classifier. Yeah. Oh, yeah, my final word on this, although I said at the beginning too, these unsupervised learning techniques, they require more finesse and interpretation, a little bit more practice and playing around. So don't be discouraged the first time you're trying them, right? It just takes a little bit of playing to understand what you're seeing. Yeah, okay, now I'm done, officially.
Any questions before we continue with the next session? Questions?
Yeah, who's next?
Hello. Could you explain a little bit more the distances between when you are clustering something like colors? There were a slide, if I remember well, that there were a little problem like how is far red, like green or something like that.
Oh, in the clustering, yeah. How you tell the distance between categorical values. Yeah, and yeah. So, and you're right. I kind of just blew through that. And part of the reason I did is because If you're using BigML, you don't have to think about it. We just do it for you automatically. But the basic idea, whoops, is, let me zoom right back to it. I can show you. Distance to a categorical. So you basically just define a distance. So you need some kind of a distance. There's no natural sense, right? You can't really order red, green, and blue. They're all equivalently distant from each other somehow. And so you use that fact to create a new distance function. So you basically just talk about, if it's a cat and you say cat again, the distance is 0, right? That's the same thing. But if it's different, then you just call that a distance of 1. Okay, so red and green are different, so that's a distance of 1. If it's red and blue, that's a distance of 1 too. If it's green and blue, that's a distance of 1. So if they're not the same, it's a 1. If they're the same, it's a 0. And then when you have multiple categories, you just basically make a new function that combines these. So you compute the Euclidean distance between a vector. So in this example, cat and dog is a distance of 1. Their favorite toy is a laser or a squeaky. Okay, that's a distance of 1. But they both like reds, that's a distance of 0. And so you just compute the Euclidean distance of those integer values. And so you'd say that's a distance of square root 2. So you basically just map them to zeros and ones. Yep. It's a little more complicated with the text vectors because they're sparse, and that's where you use this cosine similarity, where you're looking at a vector of potentially thousands of features. And so you actually just take the cosine. If you think of the cosine of vectors, it's 1 if they're collinear and 0 if they're orthogonal when you compute the cosine. And you don't use that. So you only think about positive vectors. You actually use something called the cosine distance, where you just take 1 minus. And so now you have the idea that if the same vector, if they're collinear, then you have 1 minus 1, so that's 0. And that makes sense. If two vectors are exactly the same, you call that distance of 0. And if they're orthogonal, completely orthogonal, you call it distance of 1, and anything in between is just something in between. And it's a very quick way to compute a distance function on a very sparse vector, is with that cosine similarity. But all this happens transparently. So when you put a text field in there, we create this text vector, okay, inside the data set. And if you're clustering, we do this cosine similarity for you. Yep.
Hi. This is more like a general question. I wonder if you know these two books. One is Automating Inequality, and the other one is Weapon of Math Destructions,
Okay.
Which tells that using artificial intelligence can lead to increasing inequality in a sense that, for instance, when you're using for medical insurance, for instance, then you know that people that have more possibility to get ill, then you charge them more of insurance, so therefore they can afford it, so therefore they used to get more ill. So in a way, getting out outliners or classifying credit scores or doing other kind of things can lead to like a bad image for the artificial intelligence. So it's just a general idea. Can you introduce like an ethical parameter so those things are highlighted when it happens? How will you deal with that?
Sure, I mean, you could totally do it, but algorithmically, I don't really see a clear way. You almost have to do it by policy, right? You just have to make a standard that says, if you're going to have a model that's assigning these scores or doing these computations, that you tell us something about how you did it, right? You're going to have to reveal a bit about how you computed it, which is the fundamental problem that people are having with predictive models in general. If I give you a neural network that says whether or not you can have a loan, and I say you can't have a loan, and you say why not, and I say, because the weight on this node is a 3, and that's a very unsatisfying answer to everyone. And yeah, so it has to be a bit more by policy, I think. Yeah.
You introduced and explained k-means as a way of clustering, but as far as I understand, there are a number of different ways of doing clustering,
Sure.
And I'm wondering whether you're going to build in those other approaches, or whether you've got a view on those other approaches, and how, more particularly, how one would choose between those various approaches to clustering.
Yeah. So by and large, when people are generically talking about clustering, k-means is really fantastic, and the way we've implemented it is super easy to use, and so it works for lots of stuff. But then there's lots of things where it doesn't work at all. And we do projects with companies directly that want help with specific machine learning applications, and one in particular was we needed to basically look at routes that people were driving, and we needed to cluster basically the destinations and the origins and things like that. And for that, we had to use a DB scan. I don't know if you're familiar with DB scan. but it's another way to cluster, okay, which works a little differently. It's a density-based clustering. And yeah, so there's lots of these things. We're market-driven, you know, so when enough people say, why don't you have dbScan? Then we bring it, and then everybody gets to enjoy it. But that's one that we've already used, and so you'll probably see it in the platform at some point, I would guess. I don't know if you've ever. So it's already, yeah. So you'll see that. So yes, you'll see more for sure. Yeah.
Is there any metric which you can use to compare the performance of clusterings found by these different algorithms? Or are they all so different that there's no common metric?
No, because realistically, it's when you talk about clustering, you're being so very specific about what you want it to do in the first place. I mean, the way I even introduced k-means was, let's find points that are close together in Euclidean distance. That's so specific that k-means does exactly that. And there's not a lot of value in thinking about other ways to do exactly that. If you want to say, I want to find the points that are closest together on the surface of a sphere, then that changes the problem, right? And so now you need to approach it from a different way. And so yeah. If that's what you want to do, assign points by similarity in a Euclidean space, then k-means is fantastic. It does exactly that.